Hi, everyone. My name is Pokar Rasul, and this is an academic ZNotesLive session on physics. And I am joined today by published author Kaleem Akbar, and we're going to be talking about motion in one dimension, part 2. So we'll be dealing with acceleration and distance time graphs and a little bit of problems today. This is applicable for ages 14 to 16. Hi, Kaleem. So thank you for joining us today.
Thanks very much again for the intro, Pugs. Hi there, students. We are going to be continuing from our last lesson, and today our specific goal is to look at distance time graphs, and not only distance time graphs, we are going to be looking at certain exam questions. So without further ado, let's get right into the lesson. So here you are going to be looking at a typical distance time graph that you could come across in an exam. Now here's the thing, compared to speed time graphs, these things are a little bit more rare. So speed time graphs would definitely be top of the list, and distance time graphs, whilst they come up, don't come up as much. Now, what are you expected to know, and what are the common mistakes? First of all, you need to understand that the gradient of a distance time graph gives you speed. Now, let me break that down into simpler language. What is gradient? Well, if you tuned into the last lesson, gradient is like the steepness of the line, like that part there, the slope. In math, we call it a gradient. If you think about the formula for speed, it is speed equals distance divided by time. So what does that mean in terms of gradient? Change in y over change in x. So in other words, for this 20-second interval I've got here, the change in y is 10, the change in x is 20, 10 divided by 20, you're going to see it's 0.5 meters per second. Now here's the thing that can confuse a lot of students. A lot of students will look at that graph and say, oh yeah, constant acceleration. And I'll go, no. And I'll go, why? My teachers taught me it's constant acceleration. No, your teacher taught you it was constant acceleration if that was a speed time graph and not a distance time graph. Guys, the y-axis is different. It means a completely different thing. So for example, between 20 and 40 seconds, if this was a speed time graph, it would represent, Pugs, any idea? I'm sorry, we're having some sound communication with myself and Pugs. If it was a distance time graph, a speed time graph, and you had that horizontal line, it would be constant speed. Okay, and then because it's not a speed time graph, it's actually a distance time graph, the horizontal line actually means it is stationary. All right, so you've got to really know the difference. So no gradient on a distance time graph means it's not moving. Think about it. At 20 seconds, the object had moved 10 meters. At 21 seconds, 22, 23, 24, all the way to 40, it still only moved 10 meters. So it's not moving. Then from 40 to 60 seconds, it's moved 30 meters. I've got you again, Pugs. I don't know why I lost you before. Do you have any ideas how to calculate the speed then between 40 and 60 seconds?
The speed, is that what you said? I couldn't hear you.
The speed, calculating the speed.
Yeah, so speed basically distance over time. So you do 40 minus 10 by 60 minus 40.
Absolutely. It is that trivial, and this is the thing. People get confused. They look at the graph and think, oh my God, there's a line. What do I do with it? Just like you would do with a formula, speed equals distance over time. Plug in the numbers, but understand, just like Pugs did, he can't do 40 divided by 60, for example. Now, where did I get that from? Some students will look at the 40 and they'll look at the 60 and they'll take the entire thing. No, no, no. Why? Because we're just looking at that part of the graph right there. You've got to understand there's different stages to the motion here. And here is the worst mistake, students. If I say to a student quite often, calculate the distance from a distance time graph, and you'll get this keen student, eyes light up. Yes, sir, I know how to do that. Area under the graph. And I'll do that. Because in this particular graph, you don't need to do that. And then the student will scratch his head. No, 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 it's area under the graph. It's area under the graph for a speed time graph, not a distance time graph. Here, you have a y-axis telling you the distance moved. Look, if I was to ask, look, Pugs, if I was to ask you at 30 seconds, how far, as whatever this object is, we don't care what it is, how far has it moved? In 30 seconds, roughly.
Roughly, that would be 10, right?
10 meters. You're just reading the graph. You're roughly going, okay, 30 seconds is between 20 and 40. That's why I said it wasn't very fair. But we can see the distance moved is still only 10 meters. So guys, major takeaway, gradient of a speed time graph gives us acceleration. Area under a speed time graph gives us distance. We're now looking at a distance time graph. The gradient of the distance time graph gives us speed. And if you want to find distance, you simply look at the y-axis. If I wanted to find the average speed, it would be a simple calculation of total distance, which is 40, divided by the total time, which is 60, and you would find your average speed. Now, a couple of things to point out to you before we move on to the exam questions. What happens if, I'll just sketch it on the same graph. We had it, that's not very nice. Let me do it over the side here. What happens if it was curving up? Well, I hope you understand if the line is curving up the way, the distance is increasing at a greater rate. Now that sounds very geeky. What does that mean? Well, let's just, for the sake of example, at 1 second it traveled 1 meter. Now if it was going at a constant speed, at 2 seconds it would be 2 meters. But maybe instead of at 2 seconds it was 2 meters, it was 4 meters. Quite clearly, it's covering more distance in the same time. That's why the graph is curving up. In other words, this object is now accelerating. Conversely, guys, if it curves the other way, now this is just for illustrative purposes, if it's curving the other way, instead of speeding up, it's slowing down. Now this might confuse students. They're like, well, how? How do you know? Think about this. If the horizontal line means not moving and a diagonal line means constant speed, well, you've got a curved diagonal line that's eventually becoming horizontal. If you think about here, let's look at, call this 1 and call this 2. It becomes horizontal. It was moving and then it's not moving. Well, what's happening in between? Moving, not moving? The object must be slowing down, whatever it happens to be. So guys, for me, that's all there really is to distance time graphs, you know, the basics of it. I think you're going to learn a lot more as we now plunge into a couple of chosen paper 4 exam questions from the Cambridge syllabus. Okay, so let me just clear my screen. All right, and move on. In fact, this is quickly going to summarize everything I've told you anyway. Constant speed, stationary, greater constant speed. How do I know? If you were here last lesson, remember, Pugs, how would you know? Even if you didn't do the calculation, how would you know?
It's got to be a straight line in the speed time graph. So it's got to be a straight slope, like a unwavering slope.
Okay, that's fine. But how can you tell that the second diagonal line has a bigger speed than the first diagonal line? How can you tell?
Well, let's just look at the angle with respect to the horizontal.
Okay, so that was something that Pugs came up with last lesson, which I've never come across before, which was brilliant, actually. It's great to have, you know, a student point of view. So Pugs was suggesting looking at the angle theta in there. In math geek speak, guys, it's called gradient. The steeper the gradient, quite clearly the bigger the speed. How do we know? Because the gradient of a distance time graph gives us speed. So Pugs is looking at it in relation to angle. Whatever suits you best, use what suits you best. If that's the way you'd rather learn, there's nothing wrong with it. The easiest way to refer to this in the exam that's acceptable, you can talk about steepness of the line. If that's what you want to do, you can do that. Okay? So remember, the gradient of a distance time graph is the speed. Okay, let's move on.
Yep.
Okay, I've done the calculations. I've done them with you. We can move on from this. So let us now go into some exam questions here. So here is October, November 2014, paper 3, variant 1 from the Cambridge syllabus. Okay, freely available on the internet. You can go and get yourself a copy. Now, what we are going to do, I'm just going to have to move, just give me 1 second. I'm just struggling with one thing. Right, there we go. So, guys, figure 1.1 shows the distance time graph for 3 different parts or 3 different objects, A, B, and C. In geek speak, what you're really seeing is 3 different gradients. I hope you can all see, if we're talking about it simply, object A, the gradient is increasing. What do I mean? The slope is increasing. Object B, the gradient isn't changing. In other words, the steepness is staying the same. It's a constant gradient. And if we look at object C, the gradient isn't changing with 0. Okay, it's just a horizontal straight line. So what does that mean in terms of motion? Now look, that's worth 2 marks. Describe the motion of each object A, B, and C by selecting the appropriate description. So guys, I hope you can see the A cannot be constant speed. It's definitely not stationary. Pugs, what do you think?
Increasing speed.
Increasing speed. Okay. It's increasing speed. And if you look at B, again, Pugs, I think you've got a handle on this. Go for it.
It's just constant speed.
It's constant speed. Why? The gradient is constant. Now, students, I know there's a lot of students out there that go, sir, I don't understand this because I see no numbers. Make up numbers. Stick some numbers on the graph if it makes you feel better. You can do that yourself. And then you'll see, well, wait a minute, if I was to put some numbers on this graph, that gradient isn't changing. The steepness is not changing. Therefore, the speed is exactly the same. Now, let me very quickly sketch. So, you know, maybe that's 1, that's 1. Oops, that was a bit too big. 2, 2, 3, 3. You know, you could do that yourself. I know that's a bit of a mess. Drawing's not the best. Apologies. But I hope you get the idea that you could do that yourself and see, you know what, that's not changing. Therefore, the speed is not changing. Last but not least, then C. C is stationary. There is no gradient, it's 0. And if, I'll draw this on the graph, if there was decreasing speed, what would it look like? It would look something like, I wish I had a ruler, okay? It would look something like this, where it would become horizontal eventually. So, guys, that is the 4 areas that they could test you on. I hope you can see that wasn't too difficult. And this is supposed to be the hardest paper. This is an extended paper. Okay, so figure 1.2, now this is where some students might find it difficult, because now we're making a switch. We're going from a distance time graph to a speed time graph. Remember this time, the gradient of a speed time graph. Remember, in easy language, the steepness of a speed time graph gives us the acceleration. So now we've got objects D, E, and F. So if we look at D, again, the gradient's increasing. If we look at E, the gradient's constant. And if we look at F, the gradient is 0. So this is why this is a brilliant question to choose, because this is where a lot of students go wrong. They mix up the two. They mix up distance time graph with speed time graph and vice versa. So hopefully you can see quite simply what we are doing here. So in the distance time graph, D, what did it represent? It represented speeding up. Well, it's not too dissimilar here. Here we would call it, what do you think we'd call it?
It's accelerating.
Accelerating. Is it constant though?
Doesn't look constant.
No, it doesn't look constant, because basically it's getting bigger and bigger. So it's increasing acceleration. The gradient is getting bigger. It's going up the way. We're having a steeper gradient. So students, if you imagined putting numbers, doing change in y over change in x, if I was to find the gradient, let me just draw this. Here, here, here. If you were doing rise over run, you'd have to draw tangents. We're not going to go into that today, but let's just say you could find the gradient at each of these points. It would keep getting bigger and bigger and bigger. In other words, it's increasing, so the acceleration is, in actual fact, increasing. Okay. If we look at E, I hope you understand then that that must be constant acceleration. Now remember, if that was a distance time graph, if it was a distance time graph, it would have been constant speed. Okay, the y-axis is different here. Same shape, looks the same, means a completely different thing. The thing that they do have in common is the x-axis is time. And last but not least, if you look at F, if that was a distance time graph, like on the last slide, it would have been stationary, but here it means constant speed. So it's moving, it's got a speed, and it's staying exactly the same. Okay, so I hope that makes sense. Let's move on. Now let's move on to one that involves a calculation. A typical, what I would call a more typical exam question, taken from May, June 2013, paper 3, variant 3. So look, here it's basically talking about a train, and it's saying here at time t equals 0. Now a lot of students get confused by this. What do they mean, time t equals 0? Time t equals 0 is 0 as far as I am concerned. So let's say Pugs and I, we are on the same street, right? And Pugs is, let's call it the beginning of the street, and I'm at the end of the street. And a really nice Ferrari drives past Pugs. And let's say, for whatever reason, I know he wouldn't, he starts the stopwatch because he's got nothing better to do with his day. As far as he's concerned, that's time t equals 0. Now, when the Ferrari races past me, and for whatever bizarre reason I start the stopwatch, as far as I'm concerned, that's time t equals 0 for me. So guys, when they say time t equals 0, all the examiner's saying is, look, we're starting whatever journey this is from now. So don't get confused with it. And what they're saying here is the train starts to move forwards with an increasing speed until it reaches a maximum speed at times t equals 48. So if you were to look carefully at this graph, t equals 48 is here. All right. Actually, before I move into the question, it's actually a very important skill, guys, that you learn what the boxes on the y-axis mean and what the boxes on the x-axis mean. And I'm talking about the little ones. So if you look, let's look at the x-axis, guys. Let's look between 0 and 20 seconds. You've got 1, 2, 3, 4, 5, 6, 7. This is quite small for me to see, but it looks like 10 boxes. 10 boxes. The difference between 0 and 20 is quite clearly 20. You've got 10 boxes. So how do you do this? You've got a range of 20. You've got to split them into 10 little boxes. 20 divided by 10, it means each little box is 2. On the y-axis, you've got 10 boxes, but the range is 10 this time. What do I mean by that? Let's just look between 10 or 20 or 20 or 30. The difference now is only 10. 10 boxes, 10 divided by 10. Each box in the y-axis is worth 1. It's really important because the mistakes that get made here, your students messing that up. So look, it's showing you the speed time graph for the first 48 seconds of the journey. We will come back to this graph, no doubt. Moving on. State how the graph shows that during the first 48 seconds of the journey, the acceleration of the train is constant. Well, I hope you could see that it was a constant diagonal line in geeky math speak, constant gradient or constant steepness. That's all you have to say. Key exam word here, I love this word, state. Guys, state means tell me the answer. Don't describe, don't explain. You know, you don't need to give me your life story here. Just tell me the answer. See, sometimes a student looks 2 lines. I need to fill up the 2 lines. No, you don't. I could write 2 words here and get the appropriate answer. Constant, I know I wrote more than 1 word, but the diagonal forward line there, constant, uniform, I can say either that. So constant, uniform gradient, slope, or straight line. I hope you understand that I could have said any one of those things. Okay. Then it says calculate the acceleration for the first 48 seconds of the journey. So I might have to go back for this. So if we look very carefully, that looks like 35. Guys, I am using
35.
Yeah, 35. So let's just check it. It's actually 36 then if you look at it closely. So if you go to the actual exam, because I would have taken it from the actual exam, you look very closely, it'll have been 36. What was the initial velocity? 0. What was the time taken? Well, that was easy. They told us 48. Formula, working, answer, units. I cannot stress enough how important units are. Units within an answer, without units in an answer, it means nothing in physics, guys. You will lose too many marks. In fact, let me tell you something. I don't really want to tell you it, but I'm going to tell you. If that's a Cambridge IG exam, you put in the right answer without working, with units, you get full marks. You don't need the working. Should you do that? Absolutely not. Why not? Anybody under exam pressure can make mistakes. Anybody. Put the wrong number in the calculator, daydreaming about leaving, next exam after, whatever it is. When you're under pressure, we all make mistakes, teachers included. So when you've got the formula and the working, the examiner can see that you understand. I can see that you understand. You get marks for that kind of stuff. So on to the next part. After time t equals 48, the train continues at its maximum speed for another 72 seconds. All right. So in figure 1.1, sketch the speed time graph for the next 72 seconds of your journey. Now I've done this in the next slide. I'm going to zip forward to come back. I've done it here. Okay, I did that very quickly so you couldn't see the answer to the previous question. So we know that the maximum speed is here. Now students will say to me, sir, how do we know it's at the maximum speed? Well, guys, at the end of 48 seconds, it was right here, right to that red bit. What did you expect it to do? Jump up, go down? That's where that object is. Now they're saying it stays at that speed. So what they're really saying is it's now moving at a constant speed, which happens to be its maximum speed at that time. Please don't misunderstand me. Like the Ferrari example, if it was in the street the mean pugs are in and it's going 10 kilometers per hour, I'm sure you all understand that's not its maximum speed. The car could go at, but it was its maximum speed if it was going at that speed in our street. Okay, so let's go back now, and I'm going to do this quickly again. Sorry, went back too far. The next question is asking, determine the total distance traveled by the train in the 120 seconds after it starts moving. Guys, basically they're asking for area under the graph. Really what they're saying is u speed equals distance times time. So I'm going to show you the answer now, but I'm going to explain it in the next slide. You're going to see here a half times 36 times 48 plus 36 times 72 equals 864 plus 2592 equals 3456 meters. I'm going to show you where that came from. Yep. But really, it's distance equals speed times time. That's what it really is. Okay, so you might go, well, how does that happen here? Remember, it goes from 0 to 36 meters per second in 48 seconds. So why did I half it? What you're really doing is average speed times time. You can look at it two ways. Some students they go, it's a triangle. It's 36 times 48 divided by 2. If you're happy doing that, fine. But the physics of it is actually quite simple. I started at 0, I finished at 36. How do you average two speeds? 36 plus 0 divided by 2, 18. 18 times 48, I think it was, the exact same answer as we got in the previous slide for the first part. Then we know it was going at a constant speed for 72 seconds. What was that constant speed? 36 meters per second. 36 times 72. Think about that. Speed times time. Distance equals speed times time. That is all you're really doing. If you want to think of it as area under the graph, it doesn't matter. But I want you to understand there's a simple physics to it as well. It's not really that bad. So let's move on. I want to do another example with a distance time graph. And if I'm not mistaken, this is the final example. I know we're running over, but I'm excited. I'm enjoying myself. So let's keep going.
Sure.
May, June 2012, paper 3-1. So again, it's a Cambridge paper. And, you know, I will wait for feedback, but if we want to mix it up with AQA papers, Edexcel papers, we can do that. But right now, we're sticking with Cambridge. And listen, guys, the physics doesn't change. I do totally recommend if you're on here and you're watching you're from an Edexcel syllabus or you're from AQA, you should practice your own exam papers, absolutely. It's not because the physics is different. You know, physics, speed equals distance over time and speed equals distance over time. But it's how they word the questions that are. I don't like using big words, but little nuances, little changes in how they ask it. Okay? Anyway, let's get into this. A girl rides her bicycle along a straight level road. Figure 2.1 shows a graph of her distance moved against time. Now notice they've sectioned off the graph, A to B, B to C, C to D. Shock, they're probably going to use it. So let's go on and see what they want. So they're asking, describe her motion from A to B, B to C, and C to D. Let's just go back and do those three parts. So if you look at A to B, remember it's a distance time graph. Gradient of a distance time graph gives us, Pugs?
Speed.
Good man. And the gradient here is increasing. So what do you think, Pugs? What do you think's happening to the speed here?
Well, from A to B, it looks like increasing speed. So that is acceleration. Like,
well, that's
like a mild curve.
It's fine. You can see acceleration, speeding up, moving. That's another thing, guys. See, when you look at the mark scheme, you don't have to use the exact words as a mark scheme unless it's underlined. All right? You know, students get hung up. Well, is it speeding up? Is it getting faster? Is it accelerating? All of the above. All right? So you don't need to worry about that. It's speeding up. B to C looks like a constant gradient. What do you think, Pugs, in terms of speed?
Well, yeah. Does look like that.
So what do you think's happening to the speed? I missed that.
Well, speed's not changing. That's all.
Speed's not changing. It's a constant speed. Okay?
Yep.
It's a constant speed. And then I hope you've all figured out then, if A to B is speeding up and B to C is going at a constant speed, then surely C to D is slowing down. Remember, if it's going towards the horizontal, think about it. If I had a graph that's got a horizontal line, the distance is staying the same, but the time keeps going. It's a bit like that Ferrari. Stops in front of Pugs, okay? And he's very happy. It's because someone attractive in the car as well. I'm just joking. And he's got his timer on. Time keeps going, but the distance isn't changing. Stationary, okay? So speeding up, constant speed, slowing down. So increasing speed acceleration, look, the forward slash means this or this. Constant, steady, uniform speed or motion. A lot of students get confused with the word uniform. Think about a school uniform. You're all wearing the same thing. Uniform just means constant. C to D, slowing down. Then it says calculate her average speed. Okay? Remember the formula for average speed? Total distance divided by total time. Well, that was really hard, wasn't it? It's the same formula as speed equals distance over time. Okay, it's the exact same. But we're going to take the total distance. Pugs, what's the total distance?
400.
And the total time?
60.
So all we do, sorry, we're having to do this again. Total distance, 400 divided by 60, and you get 6.67 meters per second. Here's a question I get asked a lot. Do significant figures matter at IGCSE? No, not really. Other than, why do I say not really? Let me clarify that. Practical papers, yes, and only when the exam question says to the appropriate number of significant figures. So you might say, well, sir, I have a teacher that's anal about significant figures. I hope I'm allowed to say that. It's because they're teaching you properly. What do I mean by that? Because in A level, it becomes important. But I promise you, like as a tutor, as somebody that's trying to help you ace your exam in 10 weeks, there are bigger things to worry about than significant figures. If you wrote 6.666666667 and you were one of my students, yes, you'd probably get a slap over the head, but you would not lose marks in the exam, provided you put in the units, okay? There is a time and place that it becomes important, but today's not one of them. Now, here's a question where, and Pugs, I do really want you involved because I think you might help with this. The last question's asking, what's her maximum speed? Have a look at the graph, Pugs. A lot of students would find this a struggle. Can you give me letters, if you like, where the maximum speed is?
I'm going to guess B.
Just at B?
From A to B, that's where the slope is greatest, from what I can see. Am I guessing right?
Okay. Yeah. If I could hate Pugs to make that mistake, I would have. No, thank you very much, Pugs. This is brilliant because think about what this happens to everybody. Well, not everybody, a lot of people. Everybody is too much of a generalization. Pugs is seeing, and students, I hope whoever's watching, they're seeing the gradient increase and they're like, that thing is getting faster. True. But then from B to C, we said it's going at a constant speed. And then from C to D, it was slowing down. And you're like, yeah, and? Well, surely then, guys, the maximum speed in this journey was from B to C. No way, how? Think about a car speeding up. Speeds up. Let's go back to the Ferrari because it's a nice visual. Red Ferrari, nice red car. It's going at its maximum speed. It's accelerated, and now whatever it can go at, I've got no idea, 240 kilometers, probably more, per hour. Well, now it's going at a constant speed. That constant speed happens to be its maximum speed. And this is why a lot of students get this question wrong. They're like, yeah, it's speeding up, slowing down, constant speed. They don't think that the constant speed is the maximum speed, and here it is. I hope you understand that. So let's say you're in the car with your, your parents or whoever next time. Car accelerates to 40 kilometers per hour. You stay at 40 kilometers per hour for 2 minutes. and then you slow down because you've got to the traffic lights. Well, guys, that 40 kilometers per hour was your constant speed, but it also happened to be your maximum speed. So I thank Pugs for his input. I'm hoping he did that deliberately, because that is what students would do. So guys, when we're doing the maximum speed, we're basically going to read the points B to C. So we're looking for the maximum gradient, okay? And using the correct data. Now I'm going to go back to the graph, but basically anywhere between 9.2 and 9.4. And I think I actually did it here. So how am I going to do this? Look, I've picked the point B. I'm looking at the 2 points. Well, the y-axis and the x-axis. I've picked the point C. You know, I've got my y point and my x point. What am I going to do now? Something that you do in math that you don't relate to this. You'll call it speed equals distance divided by time. In maths, you would call it m equals y2 minus y1 over x2 minus x1. Don't let me complicate it. You're finding the gradient, which here, swap m with s for speed, swap change in y for change in distance, swap change in x for change in time. Speed equals distance over time. Plug in the numbers, 350 minus 70 over 45 minus 15, 9.33 meters per second. So guys, as far as I think, yep, that was pretty much it. I mean, Pugs, if you want to ask me anything, or you think you want to go over, I know you're monitoring comments, etc. Is there anything that you want me to kind of go back over? Go for it.
Well, let's just ask the audience. Any questions, guys? You can put it up in the chat section right now. You can also send us questions to our email, or you can put it up on our Discord community. So I think with that, we'll wrap it up for today. Thank you for joining this session. Thank you, Kaleem, for being here. And we will be continuing IGCSE physics. You can follow us on Instagram or join the Discord community for updates on it. Thank you, guys. See you in the next session. Bye-bye.
Thank you.